The last part of this chapter talks about the optical activity. Seems like I need to choose the marker again. Optical activity of stereoisomers. So, there is a device. You have the picture in your book and on your study guide. It's a long tube, and whenever you add the chiral compound, the one that has R or S configuration in it, and a polarized light passes through this compound, the compound will rotate the light either towards right or left, or let's say towards R or S. That's the one of the characteristics of R and S configurations. So we call it optical activity. So we show the optical activity with positive and negative. This optical activity, we cannot determine it without doing an experiment. So you are not supposed to determine it without the measurements. We will give you the formula. You will see it in a minute that there is a formula for it. And then based on the formula and the numbers and the measurements you have, you will determine the rotation. If the rotation is positive, we call it dextra rotatory. And if the rotation is negative, then we call it levo rotatory. Okay, so we call them D, or just D or L. So whenever we have stereoisomers, they tend to rotate the light towards right or left. So we call it dextrorotatory. We show it with D or a positive sign, or levorotatory. We show it with the negative sign or L. But there is a compound which is called Meso Compound. There are two conditions that you have no optical activity. No optical activity. The first one is having a meso compound. What is a meso compound? Let me draw this molecule for you. Or same as your study guide. Do you still remember the bow tie? We have them here again. Okay, so it looks like there is a mirror in the cross section of the molecule, in the middle of the molecule. So if you fold the molecule, the two sides are the mirror images of each other. They're superimposable. When the half of molecule is mirror image of another half, so half of molecule is mirror image of another half. We call it the meso compound. So this compound is composed of two chiral centers. You remember in the previous video we determined the R and S configuration. But the entire molecule looks like it is, the half is mirror image of another half. So in a meso compound we don't have optical activity because it seems like half of molecule is rotating the light towards right or left, and the another half is going to cancel this out. So there would be no optical activity. Okay, it's optically inactive. Meso compound is optically, we call it optically inactive. Although a meso compound is composed of active centers, but the entire molecule overall is optically inactive. This is the first situation when there is no optical activity. The second situation is when we have a racemic mixture. Racemic mixture happens when you have 50-50% of R and S configuration. So what happens? Half R rotates the light towards a direction. We don't know which rotation, which direction. Another half is just opposite, right? Is S. So it rotates the light to the opposite direction. So they balance out each other. Why? Because there is exactly 50% of R configuration and exactly 50% of S configuration. If this configuration is 60-40, it's not going to be racemic mixture. The condition for racemic mixture is definitely 50-50 of R and S. Not even 51-41, not 52-48. It's exactly 50-50. So it would cancel, the half of the mixture will cancel the rotation of another half. So in these two cases, we will have optically active components, but the result, the entire compound, either the mixture or the meso compound, they are optically inactive. So if you have to choose optically inactive, you look for the meso compounds. Half of molecule is balancing another half, or mirror image of another half. Racemic mixture, which you have 50-50% of R and S. The next thing is how to determine this specific rotation. There is an equation which will be given to you in the exam for sure, and the specific rotation, which is shown in alpha, specific rotation. Is the observed rotation in degrees, and L, or let me just show it as degree, and L times C. So C is always concentration in grams per milliliter, and L is the length in normally decimeter, and 1 decimeter is 10 centimeter. Okay? Now, it takes us to this question on page 8. 12.25 gram sample of a pure compound was dissolved in 15 milliliter of ethanol. So C is 12.25 divided by 15 milliliters. Okay? And the length is 1 decimeter. And the observed rotation is minus 13.07 degrees. We're supposed to find the specific rotation. Let's plug them in. Alpha is minus 13.07 degrees divided by L was 1 decimeter times, I just didn't calculate the product of the result of this division. I'm just writing it as is. Grams per milliliter, which is 15, and it will give you minus 16. And it's asking based on the table which one of the compounds it is. It is the specific rotation will be the same for cocaine. For a cocaine molecule. So if you have some cocaine molecule and you pass the polarized light from the solution, it's going to, with this exact concentration, it's going to rotate the light to this amount, the specific rotation. All right. Now, you know about the specific rotation for enantiomers. What did we say? Physical properties such as melting point, boiling point, density are the same. But the difference is one enantiomer rotates light to exactly same value at different direction. For example, if the specific rotation of one of the enantiomers, for example, is, let's just use cocaine, 0.16, another configuration, another enantiomer is going to be minus 16. So the values are the same, but it's just one of them rotates opposite direction. For diastereomers, both physical properties and rotations are different. Everything is different for diastereomers. Okay? Now, on the bottom of page 8, you have an amino acid, alanine, S-alanine. Its specific rotation is positive 8.5. Its melting point is 297 degrees Celsius. We have a couple of questions, a few questions. What is the melting point of R-alanine? Because they are enantiomers, S and R are enantiomers, so we said the physical properties are the same, so it's exactly the same, 297 degrees Celsius. For B, how does the melting point of a racemic mixture of R and S compare to the melting point of alanine? It's different. For a racemic mixture, is different from the individual enantiomers. Don't forget we're talking about the mixture. C, what is the specific rotation of R-alanine? We said for the enantiomers, the specific rotations are just the opposite, so it's going to be minus 8.5. Part D is asking for what is the optical rotation of a racemic mixture? Racemic mixture, 50% R, 50% S. So the rotation is 0. Whenever the rotation is 0, means we have optically inactive mixture, which is racemic mixture. And finally, label each of the following as optically active or inactive. A solution of pure S-alanine, pure S-alanine. We just saw the rotation is 8.5, so this is active. An equal mixture of R and S, equal mixture of R and S. What did we just say about that? That would be racemic mixture, right? So it would be inactive, optically inactive. A solution that contains 75% S and 25% R. 75% S, 25% R, they are not 50-50. So most of the rotation is like S-alanine, but it is active. They cannot cancel out each other. We still have some S-alanine left. Isn't it interesting? The molecules can even play with the light. Okay, the last thing you need to know about this different chapter, I don't call it weird, but it's different chapter, it's different from what you had so far, is enantiomeric excess, or EE. Enantiomeric excess, EE, or we call it the same, optical activity. So enantiomeric excess is the percentage of one enantiomer minus percentage of other enantiomer. EE is percentage of one enantiomer minus percentage of other enantiomer. Oops. All right. So let's see the example, the practices. If the sample, it's given, like if the sample is 75% of one enantiomer and 25% of another enantiomer, then EE is going to be 50%, right? The practice is that, what is the EE for a sample that contains 85% A and 15% B? So 85 minus 15 is what? 70. Right? 70% of A is excess. Do you remember limiting reactant in general chemistry? Is a limiting reactant or excess reactant in organic chemistry. The example. If the EE is 95%, how much of each enantiomer is present in the mixture? We have to find out the percentage of A and B. What I do, since I would like to involve some math in it, is that A plus B is equal to 100%, right? So can I say B is 100 minus A, right? B is 100% minus A, okay? So I would say, let's call it one enantiomer. A minus B should be equal to 95%, right? Let's put 95% here. We said EE is one of the percentage of one enantiomer minus percentage of the second enantiomer. Now I would like to insert or replace B with 100 minus A. So is equal to A. Let's eliminate percentage now so we won't get confused. A minus, what do I replace for B? 100 minus A, right? It would be 2A minus 100, right? So 2A minus 100 is equal to what? 95. So if you solve it, 2A is 195, right? And is it? Yeah. So A is 95 and B is 100 minus 95, which is 5. Give me 1 second. Okay. It's the 20. sorry, I was working with the 90%, the second example, sorry, 190, then it's 90% A and 5%. And you can do the same thing for the first one to find, so don't forget, this is the second example. Second example. So you can do it for the first one also. You have another way to find enantiomeric excess, EE, from the rotation. It depends on what you have available. It's rotation of mixture, rotation of pure enantiomer times 100. So in the next practice, a pure enantiomeric compound has a specific rotation of positive 3.8, the pure, and it's 60%. 60% is 60 over 100 times 100, which gives you 15.7. Okay, I hope this lecture was useful, and don't forget to work on all of the problems in your book, the end of the chapter problems, and study this study guide, which is really helpful. Let me know if you have any questions.